Created using Powtoon. Created using Powtoon. Created using Powtoon. Created using Powtoon.
welcome to Teaching Physical Sciences. Today we're joined by Annabel. Hello, Annabel.
Hello, Helen. How are you?
I'm good, thank you. How are you?
I'm well, thank you.
Now, I'm sure we're related somewhere.
Yeah, we're almost sharing a surname.
Almost. As Robertsons and Roberts, yes. We should stick together.
Yes.
Yes, and of course we have Dylan behind the buttons. Welcome, Dylan.
Hello.
Always good to have you. Now, today we are talking about teaching grade 10 motion in one dimension.
Yes.
I have been practicing that a lot because I keep saying one direction.
Which isn't very different, really, because in one dimension just means stay going in one direction.
That's what I thought.
Yeah.
But then my science friend got quite upset with me.
If you're going to look at it with very critical eyes, yes. There's a subtle difference. But really for kids, it's perfectly fine to say the car is going in one direction. It just means that there's no depth to the motion of the car.
Okay, so I'm reading between the lines here, and I'm reading that I'm understanding it on a kid's point of view,
yes.
And really I should be raising my level.
You understand it perfectly as a kid should.
Oh, good. Now this is the first time you're with us.
Yes.
Thank you very much.
It's quite a privilege, and thank you.
Would you like to tell us a little bit about yourself?
I have been teaching for 20 years. I've taught both in government schools and in IB schools, and I have done quite a lot of work in terms of developing the current curriculum. I was involved when the IB put forward some of the ideas on this curriculum, and so I know it quite well, and I am actually quite fond of the changes that have been made. I love being in the classroom, have been teaching 10, 11, and 12. That's what I focus in on. And thoroughly enjoy teaching. And I've loved all the innovations and changes that have come with teaching along the way. I've taught here in Gauteng. I went up to Limpopo for about 3 years, and now I'm back down in Gauteng and
welcome
enjoying
back.
it. Yeah, so that's me in a nutshell.
Is there a big difference between IEB and government in terms of the assessments?
I don't think... I think people sometimes look for the difference instead of the similarity. I think there's a lot of similarity. I think the vast majority of the core... Remember that the IEB are obliged to use the caps. They're obliged by law to follow the caps.
Okay.
And all that changes is a subtle emphasis, really, in terms of what's going to be assessed and how it's going to be assessed. And it is subtle, and I think we should be sharing resources more. I think people are frightened.
Are you speaking my language? Yes.
I think people are frightened when they see something's designed for the IEB that they can't use it in a government school and vice versa. And I don't think that is valid at all. I think we should be sharing and using each other's resources as much as possible.
I completely agree. Remember that you should be talking to us on Twitter using the hashtag #MEScience. Or on the Facebook page, search for Digital Classroom South Africa and then find the post. Dylan will be watching both Facebook and Twitter. He'll also be watching the chat window, which you'll find just under the box that you're watching us in. So if you scroll down a little, you'll see it says enter your nickname. Choose something that's interesting, not something boring. And then log in and start chatting. And of course... if you chat to us, you could possibly win 110 Rand Vodacom airtime, and that's always nice.
Useful and handy on teacher salaries.
And on that note, with sharing resources, which is one of my favorite things, because if someone shares something with me, it means I don't have to make it.
Yes.
Yes. So if you have something that's awesome that you want to share with us, do, because you can win a phone or a tablet.
All you need to do,
it is great. I get excited. They're all sitting in the cupboard waiting to be won. So you need to enter your resource. Watch out for the secret code that will appear at the bottom of your screen at some point during today. Write it down, then send your submission to competitions@digitalclassroom.co.za, and we'll look at them. Okay. Now, Annabel, I have been reading this book called Teach Like a Champion.
Yes.
And it's got 49 steps in it, or 49 techniques that people can use. And the more I read it, the more I get irritated, actually.
Okay.
Because a lot of the steps are about conformity. But there are some really, really good tips in there. And I think what the book is trying to get to is that there are certain practices that a lot of teachers do because they work.
Yes.
And because you can teach better. So we've been going through step by step, and today we're on step 15.
Okay.
So I'm about a third of the way through. And this step is called circulate. Move strategically around your room during all parts of your lesson. I really like this one.
It's fantastic. I really try so hard to walk around, so much so that on an evaluation from my students, a couple of the girls in the front row said, sometimes you can come and stand in front of the room. But you target discipline problems so easily if you move around your room.
Before they even happen, you've got them.
Yes, and also the in terms of being different, students are so used to now with TV and stuff, with everything changing all the time. If you stay static, their lesson is static, their lesson is boring. You just moving means that they've moved their head around and they've done something, and then that, I think, it seems to keep the audience a little bit more in rapture. And I can see if they're moving their head around or not, and then I can see whether people are paying attention.
I completely agree.
So, yeah, I think that that's an awesome tip.
And it really does sort out a lot of discipline issues before they happen, as well as you can go to people who need remediation but don't want to stand out from the crowd by putting their hand up.
Correct.
You can spot that as a teacher. You know where they are. You just go and float over there, help, and then carry on.
Absolutely. And particularly in a subject like physical science, where a lot of their time in the classroom needs to be spent practicing, that is a chance to walk around, a chance to integrate yourself into them. And I've actually got to the point where I'll often pull up a chair, sit next to a student that I know is having difficulty, and give a little one-on-one lesson right there and then.
Yes, get it fixed before they go home and carry on that problem over and over, or that misconception, rather, over and over.
Absolutely.
Yes, Dylan had some wise words on this moving around the classroom. Dylan, please share.
Okay. Some wise words. Well, someone once said to me that there were 3 positions in the class. There was the position that's up front, where you deliver general instruction, general teaching. It's probably the worst position to remediate from, and it's probably the worst position to discipline from, because it simply creates a spectacle. The next position in the class, they said, was the middle distance, and that's where you're in the midst of the learner body, but you're talking to a group of learners. And that can also be really useful for providing instruction, but also asking questions for assessment purposes. As a group, do you understand what I'm doing? Who of you need extra help, etc., etc. Not so good for discipline either, because again, the platform is a little too public. And then there was the close-up distance, where you're right next to a learner. Maybe you're pulling up a chair. And that is excellent for remediation, one-on-one work, but it's also the best position to deal with discipline issues, because you're not raising a spectacle, you're not calling attention to somebody unnecessarily, and you can say, listen, if you do that again, we're going to have a real problem.
He's got a good, scary face. Well done, Dylan.
Yeah, you've got scary. Obviously, a good, scary voice. And it's something that teachers need to practice.
Absolutely.
In a sense, I mean, I was sometimes told that as a student teacher, when you're issuing instructions or when you're talking to learners, practice the stuff in the mirror.
Yes.
And it sounds like a really silly thing to do, but it does work.
Very definitely. And also, when you're issuing instructions, don't say please. It's an instruction. It's not something to be polite about. Take out your book. Not please take out your book.
And also to perfect the stare. There is the stare.
It's a really good skill. I find myself using it in shopping centres occasionally.
I think we should have a competition. Send us a picture of your best teacher stare.
Yes.
That sounds like a brilliant idea. See, we'll decide which one looks most scary.
Yes. And then we would feel obliged to give them something, because it'd be, don't you? Okay, shall we look at your 5-point teaching strategy?
Yes.
Now, you've chosen to talk mostly about the graphs within motion in one dimension.
I have, because I feel that it is in the graphs that we get to visualize the motion, and it is in the graphs where there are the most misconceptions. So that is why I've decided to focus in on it. Motion in one dimension, I take 6 to 7 weeks over teaching.
Okay.
And so when I was presented with an hour, it really wasn't, it would not have been meaningful to try and address the entire topic. So I've zoomed in on a section that I feel you can teach really, really well if you go through the steps nicely, and you can get it well embedded into the student's knowledge. And it's important that it's well embedded because of the fact that these graphs still continue when you do Newton's laws later, when you start looking at energy relationships later, when you start looking at momentum later. This is the foundation on which all of that gets built.
So it's an important section then.
It really is, and it's taught in grade 10, but it's really the beginning, the real beginnings of matric, because so much gets built on top of it, and the skills need to be moved and used again. Yeah.
Okay, your first one says use real props to convey ideas.
Yes, we as science teachers have a beautiful picture of a lot of things in our minds.
Yes.
One is we can see atoms quite clearly. We can see them moving, and we can also see a car going at the same speed.
Yes.
And we can see a car going up a hill, and we see the picture. The students don't see the picture. They're used to a television giving them the picture. And so it's so important that as simple as a topic is and as simple as a concept is, for us not to say, now just imagine a car going on a straight road. Much better to pick up a car, as small and as simple as it is, and to say, right, if this is going straight and I keep it going at the same speed, can you see? And from seeing something real, they can now join in the conversation. When you put it into the space of the imagination, they can't join in the conversation because they're not imagining what you are.
Yeah.
As comfortable as you are in your space is as they are. They're not with
Someone
it.
actually came in and cited the same problem about the picture in your mind is not necessarily the same picture that they've got. And the sign of a good lesson is when the students walk out with the same picture in their head of what you've done.
Yes.
And so using props is a good way to get that done.
I feel that as simple as the prop is, even if with all of science, if you can just get, my favorite experiment of all time, and the kids laugh at me, is my child gave me an acorn, which said, please use this in your teaching. So we always drop an acorn, and every single time I say, oh, look, it worked. But I drop that acorn 100 times over to keep illustrating points. I throw the acorn in the air.
Yes.
We could imagine it just as I am now because I don't have an acorn. But if I've got a real thing, they can go with me. And that's so important.
It's also something to tie the memory to.
Yes, I suppose so. Now, if we're looking here at this orange car, the orange car is going to stick out in someone's mind. Oh, yeah, remember when that little orange car did the following? Or remember when Ma'am arrived with a bag of 12 cars and we got into pairs and we started playing with the cars. Yeah.
Yes.
And that's fun.
It is. Okay, your second point says collect data that will give the desired result. That's quite a loaded statement, isn't it?
It so is. We obviously, in real science, would like to be objective, and we'd like to conduct an experiment and then see the results and then deduce why those results became as they were. The science classroom at grade 10 level is not a PhD thesis. Objectivity is not what we're looking for.
So by objective, it means we don't have preformed ideas.
Correct.
Okay.
We have very preformed ideas. We have a textbook. We have a picture that has to come out the other side.
Yeah.
We have an exam that needs to be answered. And therefore, to try and reinvent the wheels by the students discovering things from data that's going to be riddled with errors is just setting oneself up and the students for failure.
Why would it be riddled with errors?
Because invariably, for example, if I'm going to try and make something move at a constant speed, my statistical chance of getting that right is pretty low.
Yes.
Friction's going to get in the way of it. If I wanted to accelerate uniformly, well, I'm going to have an absolutely perfect frictionless plane. You don't get a frictionless plane.
No.
So invariably, also in schools, we've often got old equipment that's supposed to, a ticker timer, for example, that's supposed to have a frequency of 50 hertz, but actually is working at about 32 hertz.
Yes.
And so you land up with more and more curveballs that are going to make your data not look like the predicted values. My personal belief is start the students off with the familiar, with how it should look. And if after that we want to go into looking at real data and then trying to identify error, but if the first data they get doesn't fit the graph, they don't even know what graph to start plotting. They don't know whether is that supposed to turn out to be a parabola or a hyperbola or a straight line, or must I just play join the dots? And they just get completely confused. And the concept of a best fit line at grade 10 level is really quite a tall order. So I try very hard to start with data that they are going to find works.
Okay.
And from there, start looking at why it might not.
So when you say collect data that will give the desired result, you're actually saying give them data that gives the result.
Yes, I suppose that's probably better in the sense that I've collected data.
I did this experiment at home.
Yes.
And look.
Look what happened.
Yes.
Yeah. So that's what I do feel we should be doing, yeah.
Okay, the third point says, Dylan, you have a question. Yes. Or a comment.
Well, yeah, perhaps to challenge that in a way and say, you did say a couple of times at grade 10 level. Is this something that you believe kind of we need to loosen up on as learners move to grade 12? And how do you, in that context, how do you balance getting kids to understand the concepts you need them to understand so they can answer the exam papers, but also getting them to understand how science works? Because science is not clean and clear. Science is difficult and messy and frustrating. How do you balance those, and aren't they both important?
Absolutely, that they're both important. And balancing, I think, as with absolutely everything in life, I'm not sure we ever get it 100% right.
Yeah.
We walk the tightrope. I feel so strongly about making students understand that science is not actually in little boxes at all, and that it is continually up for debate and change at the edges of science. And also, by the matric exam, they're going to get asked, why is this data not as it should be? So we definitely need to start working towards them being able to give explanations of friction, or we were on the planet Jupiter instead of the planet Earth, and the person was not pushing with a uniform force, or those kind of explanations are expected by the time you get to the higher order questions in
I was just
grade
about to
12.
say that's the analyzing and the applying.
Correct. So we cannot just ignore it. We can't just give them perfect data, ask them to plot a graph and say, oh, goody, we taught graphs of motion. It's so important that once we've got the foundations laid, that we then interrogate disparities and discrepancies and all of that sort of thing. And that there has to be a why. Why the universe is not behaving as it should, there must be a why. And they've got to start asking those questions. At grade 10, it's better, in my opinion, to start with, this is how we'd like it to look, this is why we'd like it to look that way, and then start exploring real-life examples. Whilst the textbooks very often are coming in from, let's play with a ticker timer, let's get this absolutely confusing piece of mini toilet paper and then not know what to do with it. So, yeah.
I remember having lots of fun with our ticker timer tapes after the lesson.
Did you make necklaces? Did you make those cute little foldy things?
Yes, we did. And then we had... we tried to get the longest piece without the science teacher seeing, and all sorts of... I went to an all-girls school. We had lots of fun.
Great.
Okay, number 3 says draw position versus time graph, velocity versus time graph, and acceleration versus time graph, all from the same data.
Yeah, I really feel that one of the skills that doesn't translate is the translation between those graphs. That a position time graph for the exact same information will look different to a velocity time graph to an acceleration time graph, that they've got to understand what's on the axes. And we're going to take a look at some PhET simulations later on, which very, very nicely illustrate that, which show quite clearly that when you've got a curve in the one, you've got a straight line in the other, and you've got a horizontal line in the other. And what does that mean?
Yes.
I feel that students come very ill prepared in terms of what does a graph really mean. In the maths classroom, they are taught X and Y, and they have to be able to get a equation out of 2 points, and they may be quite skilled at that. But it doesn't mean anything in real life. So that, I feel, is a skill that in the science classroom, we need to show them that they've got to actually read that the axis doesn't just say X and Y. The axis says time and position, or time and velocity, time and acceleration. And what are the differences in that? What is a gradient really telling us?
Do you find that they struggle to apply the math skills in science, or do they transition that quite nicely?
They're quite convinced that every classroom is in its own little capsule and that there should be no cross-pollination. So you really have to draw it out of them. Do you remember, have you heard of y equals mx plus c? And by then they've changed it in the maths curriculum, and they're using some different symbols. So...
and then you come across looking like you don't know what you're talking about. Yes.
Yeah. So, but you really do need to reteach the maths.
Yeah.
Obviously not to the depth. It does ring bells, and they do get, I remember. But initially, you have to spend a bit of time reteaching some of the concepts from the maths.
If you're following the CAPS curriculum, it means that functions would have been taught a few months ago.
Yes.
So they'd need some revision. Would you work with the maths teacher to maybe get the maths teacher to say, remember you're doing this now in science, or...
I think that would be ideal. I have to confess that not really. And I just started, and they generally are there, and they dock in quite easily. I have had some maths departments who've decided to teach things in a very different order, and then you land up in a situation where the whole class looks at you like this.
Yes.
And then it's down to the staff room, and have you taught straight line graphs and functions? Oh, no, I'm getting to that next term. It's not so helpful. Yeah.
I know with trigonometry for a while, it was taught after it was done in science, and then you're dealing with misconceptions from the science teachers.
Oh,
yes. I'm sure you weren't one of them.
Couldn't have been.
Okay, then number 4, determine gradients and area under the curve and see connections.
In terms of when you've now worked with the identical data, you'll start to see that your position, so the final displacement or distance covered, will, when you work out the area under the velocity time graph, it's going to land up being the same number. And that's part of the discovery that the students go through when they work through data. And I'm going to work through it in a second very quickly, but that they get to the point of going, oh, wow, that's the same. And when they get a velocity as a gradient, they can see that that was the constant velocity that was used all the way along. And that's the power, I think, of using the same data through all 3 graphs, because you can then see the links. And eventually in an exam, they're not going to have to plot the graph in detail. But taking the time to plot it at the beginning is what is going to solidify the concepts that they are able to translate between the different types of graphs under exam conditions, and realize, oh, of course, yes, that was the same number, and that makes a bit of sense.
Okay.
So I really feel that using the same data and then trying to do graph interpretation from that is very, very helpful.
It makes sense to me.
Good.
Yes. And lastly, put the picture or graph into words. Describe them out. Now, this is what I'm thinking while you're saying that. When you say that the area and the something else, you find out that they're all equal, and the student goes, aha, but is it an aha because they're equal? And you go, okay, it's the same number, or is it an aha because I understand why it's the same number?
I think 50% of the students are in the first category and 50% of the students are in the second category. I think understanding why it's the same number is higher level thinking. it is a gain, in truth, you're really starting to talk about derivatives and stuff like that as to why they come out the same, which is really matric maths work. It's tough. So just seeing that there are congruent numbers is one step in the right direction. A real understanding, and this is where we're back into higher order thinking, is being able to describe motion off the graph. And again, when you know what your axis means, that is when you are able to start making descriptions. You're not just seeing a straight line going up. You're saying that is a straight line with relation to the speed or the velocity of that particular object.
Now, is that something you can teach, or is it intuitive?
I think you can teach it. I mean, you can drill it for a long time. If this graph does this, then that's what you will say. But I don't like to teach it like that at all. I like to talk through a lot of graphs. And get the students to describe the motion to me, and I always put it at the end. Do you put it in
context, or will you just say, what is the motion that's happening here, or will you say, there's a boy running down the field?
I think what happens invariably is, because it's a higher order thinking question, there will have been some basic calculations off a certain graph. Okay. And then it'll be describe the motion between points A and C. Describe the motion from here to there. And they're now sitting with a velocity time graph, and they need to say what has happened in terms of changes of position, what has happened in terms of acceleration, and so they need to be able to know how they move between each other.
Okay. 3 pressure points. The first one says students really don't know what graphs mean. They can draw the lines and possibly even get answers, but they do it by some formula and without understanding. Now, in the maths classroom, this is not really such a big issue. If you can answer the questions, you do this. Maybe there are maths teachers out there who will disagree with me, but you don't have to really understand what the graph is telling you without working with it. But it seems to be a problem here.
Well, again, we have to get to the point where they can answer the level 3 and 4 questions. We have to get to the point where they are able to describe what is happening. They need to be gaining meaning out of the graphs, and they don't. So they get a velocity time graph, and how am I going to get the displacement? I'm going to calculate the area underneath the graph. And how am I going to get the acceleration? I'm going to calculate the gradient of the graph. But they don't understand that, well, obviously gradient is change in y over change in x, which means that I'm looking at the change in velocity over the change in time. What is the definition of acceleration? The rate of change of velocity. So it is change in velocity divided by a change in time.
Yes.
And now it has some meaning.
Yes.
And I feel that is sorely neglected in the teaching of graphs. It's really, or graphs of motion. In a science classroom, I feel that we're so busy trying to get them to be able to calculate the area under and calculate the gradient, and know that for a position time graph, you're going to get a velocity as the gradient. And we drill that. But actually, if we get them to understand the graphs from the beginning, there's not that much drill work required, because it's obvious by reading the axes and knowing your definition of acceleration and velocity that you can easily work out what you should be doing with that information.
It is the first time I've heard it explained like that, and it's the first time it actually makes sense to me. I actually have a bit of hope now that I might be able to remember something. But even if you remember the definition of acceleration being the change in distance,
change in velocity over change in time.
If you remember that, then you can remember which goes on which axis.
Correct.
Your gradient formula is change in y over change in x. So
correct.
Yes.
And so again, when they gain an understanding rather than just doing things by rote and remote, I feel that you have won the battle of rote learning. I'm opposed to rote learning, and I like the strides that the physical science curriculum has made in terms of much more broad brushstrokes and application. I mean, years ago we had to learn specific chemical equations and things like that, and I didn't see that as science. That was mastery of your memory, and the more we can get them to understand, the better for me.
Yeah.
Yeah.
Okay. Next one. Students have no idea how to interpret data from ticker timers.
Okay, so that's my little bugbear, really. Ticker timers are widely prescribed in textbooks. Ticker timers aren't necessarily widely available in schools, so that's my first sort of concern about it. But even from there, ticker tape involves you needing to understand frequency. The concept of we're not actually interested in the dots, we're interested in the spaces between the dots. So you need to always be counting spaces.
Yes.
When you're working out averages, you need to chop your first section in half and your last section in half. And why do we do that? The students all want to know. And it's because you're working out an average and what's the most likely point of reality for that. And that would be the midpoint. And so you work from midpoints to midpoints. Those are all really difficult concepts. And all of that effort only to be able to get data that probably isn't going to graph very nicely. So you spend hours and hours hoping to tweak your information so that you can teach them graphs. Because all you really want to do is teach them the graphs of motion.
Yes.
And there's this one prescribed experiment that is actually so riddled with possible pitfalls.
Well,
Yeah.
like?
So, well, the possible pitfalls start with the fact that often the ticker timer machine doesn't work. Then your carbon paper keeps flying off, so you've got halfway through the experiment, and then the dots are no longer being made.
Yeah.
And then you've got problems where the ramp doesn't, to try and compensate for friction, you have to get this ramp at some magical yet unknown angle. And so it's an absolute exercise in trial and error and measurement and remeasurement. And
So the angle isn't predetermined. There's not
No.
someone out there that knows what it is.
because it depends on the surface each time. So let's say you have a nice steel ramp. It's got far less friction than somebody who's got a wooden ramp, which has got less friction than perhaps somebody who's got a very old wooden ramp. So you have to sit there and tweak it for yourself.
Yes.
And I suppose it also depends on the vehicle that's travelling down the ramp.
This is your next.
How well oiled are the wheels?
This is the next problem. Are they made of steel or are they made of wood or are they made of rubber? And so you go with so many variables that are going to alter the outcome of this experiment, coming out with data. There's a difference between data from an experiment and data that we're going to use to teach. And I think what I'm saying as I bring this forward
Yes.
is that I would like to teach the concept with ideal data.
That's a really good point to make. The difference between the data from an experiment and the data you use to teach a concept, not cheat.
Yeah. Well,
Yes.
I think that might have been a Freudian slip because
Yeah.
when we're teaching, when we're diddling the data to teach a concept, we are cheating a little. But it certainly helps the students. And at the end of the day, that's who we're in the business
Yes.
for, even if it means tweaking our results just a little.
Yes.
But I do feel that the exploratory nature, after they've got the foundations in place, and then saying, this is your real data, explain it, is very valid.
So it's a case of, at that point, explain why your real data doesn't look like
Exactly
the data
that.
should. And from that come discussions of friction and
Correct.
the fact that the frequency of the ticker tape wasn't actually what was written on, that we're measuring with a ruler that isn't perhaps very accurate.
Rulers are generally quite accurate, Dylan, but the other mistakes, bigger.
Well, in terms of, it's a dot
Yes.
that could be smudged on the ticker tape.
Absolutely.
Do you measure from the start of the dot, at the end of the dot?
Absolutely. Especially once you start blowing up your ticker tapes. So there are all these worksheets with blown up ticker tapes, and then the dot is almost a centimetre in its own right,
Yes.
and where are you measuring from? Exactly. Yeah.
Okay, your last pressure point says students cannot distinguish between velocity and acceleration.
No,
This is something I struggle with as well. So
They just, grab whichever one. And this pertains to when they're doing equations of motion as well. That they see an M, a dot, an S, and a little negative sign.
Yes.
And they're not really sure. And they plug it in anywhere, you
Yeah.
know. There's kind of 5 meters per second? How's it different from accelerating at 5 meters per second squared? And of course, they're actually wildly different. And when you
Yes.
start playing with simulations, you can see that it's completely different, but they look too similar. Their unit looks too similar. Their numbers are in similar ballparks, and students really do just grab at a number in the hope that it's going to fill the hole without understanding that when you've got acceleration, and it's kind of the order we teach it, because acceleration means there must be an unbalanced force. We only do Newton and his forces next year in grade 11. You should have touched on it somewhere in grade 9, but many people haven't because they didn't even have a physical science teacher in grade 9.
Yeah.
They did a lot of nat sci, but it was life sciences.
Yeah.
So you do need to introduce just the idea of forces, and that a force, an unbalanced force, produces acceleration. And acceleration is when the speed, because now we use this word velocity, it's not part of their language. So especially once I'm going into one dimension, once I'm working in just one dimension, why do I want to give it a vector nature? Okay, there's a positive and a negative. You could be going backwards or forwards. But in terms of a lot of the time, you can just use the word speed to convey the message of what you mean. So if the speed is changing, you are accelerating. And if they use the word speed, that's a word that they can access. You're using the word velocity, which is confusing in its own right, and now you're trying to use a confusing word to explain the word acceleration, which is also, because in their language, they've sat in a vehicle and it's moved. Yeah, it's speeded up sometimes and slowed down sometimes, and and that it's all very vague and nebulous. So bringing it down to as simple as possible for them to learn the concepts. Yeah,
It almost sounds like you need to have these definitions written down, a little cheat sheet.
absolutely. While teaching this, I have graphs of motion, equations of motion, posters up in my classroom on my board during the section, so that we can continually refer back to what was the definition of, because otherwise they become confused, and you don't want them. I'm going to just go on to a chemistry thing,
Yes.
but I have all the polyatomic ions sitting up on my wall. I don't want them to get in and stumbling because they can't remember what sulfate is.
Yeah.
They can stumble in an exam when they get to that, but in terms of working in my classroom, I want the information to be easy for them to access.
Yeah.
And so putting it up on the board is a brilliant, brilliant idea.
It's almost like a clickable link on a website. You go, oh, I don't know what that is. Click it quickly. It's there. Okay,
Yes.
I can go back to
Yes.
the rest of it.
Yes.
Yeah.
It's giving them the tools to be able to engage with the material meaningfully. Yeah.
Okay, now we put down at this point we're going to play.
Yes, let's
Yes.
play. It's not a very difficult game. I'm
good.
I'm going to count to 5.
I'm quite competitive, so watch out.
Okay, no. It's not a game that you have to win or anything. All you have to do with your pen is follow me, and I'm going with little orange car over here. Okay, and we're going to, when I say 1, I think we need to choose a point on the car, because otherwise I think Dylan might be upset over there. So we're going to go with the front wheel. And
Okay.
as I count 2, you're going to put a dot. As I count 3, you're going to put a dot. So with 0,
Yes.
put a dot.
Okay.
Yeah, quite a significant, something we can see. There we go. Or, like a
Well,
little
now
line.
I've made it too big. And I'm going to do a line.
That's a great idea. Okay, so let's go. 1,
No, man.
2, 3, 4. Okay. Can we see that when I move this car at more or less the same speed, we have more or less the same size spaces between these things? And even the two of us, accomplished professionals, apparently are not so good at getting perfect data.
I don't know what you're talking about. If you scrunch up your eyes, they look exactly equal.
Can you get a red pen? Right.
Yes.
And we'll start at the same point.
Okay.
And this time, I'm going to try and speed up my car. All right? Are you ready?
Yes.
1,
Ah!
2, 3.
Now the cable's in the way.
I'm sorry. Okay. But what we're quite clearly seeing with the red data is that small, slightly bigger, and even bigger. Except for this sort of minor cable error over there, so we'll put the red line here.
Okay.
Okay, quick. Yeah. Good stuff. Okay. And already students are now seeing what we wanted them to see on a ticker timer on a piece of ticker tape, the dots are getting further apart when I'm speeding up. And if I were to start fast, so let's just rewind it from this side. So if I was slowing down, the dots would get closer together.
Yes.
And if I was going at the same speed, the dots would be in the more or less evenly spaced. So you land up in a situation where the concept of expanding distances, when you're accelerating, more and more distance gets covered in each space, can now be explained. So they sit with their own piece of paper, like a nice A3 piece of paper, or you give them chalk. It's quite nice to just go out into the car park and everyone has chalk. And they make markings, and they work in groups of 3 or 4, and they make their markings of moving it at the same speed, of speeding it up, of slowing it down, and seeing what's happened to distance covered in periods of time as we are going at a constant speed versus going at a speed up speed versus going at a slow down speed. Speed up, positive acceleration. Slow down, negative acceleration, which in English we say deceleration, but science likes negative acceleration because it's a vector. And then the same thing with speed. We're going to sit there and we're going to say if we've got a constant speed, that's the same change in position for every second that goes by. And now they've visualized it. They've seen it.
And you would do this after you've worked
I would
with
do
your
this.
graphs.
No, I would do this right at the beginning. Starting
this
point.
This is your step one. Play with the props.
Playing with some props, just getting them into the feel of motion and making them play. I feel it's so important that there's a tactile aspect to lessons.
Yeah.
And it's going to take us after this little bit of play, which is 15 minutes in the car park, taking them to play in the traffic. At that point. You're going to then spend 3 hours in the classroom, So the play's small, unfortunately, but that is the reality of getting students through exams. But they must get that little play to start with. And they must be able to see changes in position in terms of relations to time.
Okay.
So that's important to me. I bought a rocket.
I
just
was
want
about
to
to ask, why the rocket?
Because what we also land up doing eventually is we talk about projectile motion, and it's covered particularly in grade 12, but there's no harm once they've mastered some of these concepts in talking to them about rockets going up, stopping at the top of the projectile, coming back down, and all of that sort of idea. And I like my rocket because it gets used quite a lot. So I just thought we can bring the rocket as well. And the other thing that I wanted to show you is that when we have a slow car and a fast car, that we can also talk to them a little bit about relative velocities, about what sort of a speed do each of these cars experience as they approach each other. So if this was coming towards at 20 meters per second and this was going at 10 meters per second, both of these vehicles would feel the other car coming towards them at 30 meters per second. And that's why a head-on collision is so dangerous versus 10, 20 catching up only at 10 meters per second. And so that sort of play when we're doing vectors is also really, really helpful in terms of relative velocities. Again, we had the picture in our head. Until we bring the toys out, the students don't.
Yes.
So...
I think about the cars coming towards each other every time I'm on the highway. So it haunts me.
The good part about being on the highway, the big highways, is that you can't go and have a head-on collision.
Thankfully in Joburg not.
When you're in the center of it's when you're traveling between towns and you're on a double carriageway and you have to overtake to get past a slow truck or something. And that is the most dangerous driving. And hopefully by the time they finish motion, students have some concept of how alert they need to be on the road and how forces can make a big difference and how careful one needs to be. Because when you start doing the calculations, it's absolutely frightening. Not wearing seat belts, it's quite a story.
And of course there is a section in that later on,
yes,
isn't there?
Newton's laws, we spend a lot of time on it, So, but this is the start of it because this lays the foundations for Newton's laws anyway. All right.
Okay, now you brought some of your doctored numbers in with
I
you.
did. So here's some fake numbers.
And we'll post this on the blog.
Yes, super.
So that people can use them.
With absolute pleasure.
Thank you.
They are not 100% perfect because I do want to introduce the idea of best fit lines. So first here we've got time and we've got displacement. And
I'll hand you the mouse.
thank you very much. So that has been plotted over here. Can you see that this point over here is slightly off
So
the
it's
actual
the
curve?
second red cross from the top.
Yes, correct. The second red cross from the top is slightly off, and that was deliberate. You know, if I'm going to go back here, you can see that these don't go up in absolutely perfect increments. It should be 1.5, 3, 0, 24. So I've made this data just fractionally imperfect to start introducing students to the idea that it may not always turn out absolutely on
Yes.
the line, as perfectly as the maths class does, let's say.
Yes.
Okay, so they're then going to plot their graph. They're going to put time, and I find this a really good time to start reminding them of independent and dependent variables.
Yes.
Of saying, I chose the times. I counted out 1 second, 2 seconds, 3 seconds. And in this case, maybe my stopwatch stopped on 2.4, 3.1, but I chose the times. The word independent starts with an I, and I
That's a good way
decide
to remember.
what's
Yes.
going to happen there. The independent variable is then going to go on my x-axis, and whatever my measurement is, my dependent variable is always going to come out on my y-axis. So it's a good time to reinforce those. And then it's the graph of whatever is on the y-axis versus whatever is on the x-axis.
And labeling is important.
It is so important. It is worth marks. And, I mean, it's set at low-level questions, but the number of marks that get flushed away
Yes.
in exams when students don't do the labeling of a graph. It's so important that the unit is there, that the full name is there. And the other reason why I use slightly unideal numbers is that these are not the numbers to put onto your axis. When you're labeling an axis, you need to evenly space this. So it's 1, 2, 3, 4. Not my 1.5, then 3.1. The axis has to be decided with a minimum and a maximum value in mind, and then even spaces. You're plotting the points happens as an afterthought to that.
Okay.
Because what students so keen to do is write 1,5, 3,1, 4,4 and go from there. And that is not how you do it at all. The same true on my y-axis over here. So if I go
Very
there,
good point.
again, I need to max out at 12 and I have to start at 0. This 0, 0 point, hugely important. It tells me what I'm measuring everything else against. It's in relation to that point that every other measurement is being made.
Yes.
And obviously at 0 time, I had made no forward progress.
Yes.
So that's a reasonable point to put on that graph. Now we have to focus on doing the gradient, and they're hopeless at it. Really, truly, it's a very painstaking thing where I literally stop them, make them take their pens, put a big dot anywhere on this line, and I won't let them put them on the red dots. So that they can understand that the gradient is true at any point of the straight line. Well, at any 2 points of the straight line,
Yes.
but it's true for a full straight line. So I make them choose any random point. I make them label them number 1, label them number 2. And then painstakingly go y2 minus y1.
Yes.
X2 minus x1. And put that step in very clearly for themselves. And then calculate the gradient from there.
They get muddled quickly with that Y1 and Y2.
Which is why I love to label the 2 points. And, it doesn't matter which one's higher, which one's lower, and it really doesn't matter where they are on the line.
Yeah.
So that's helpful
Yeah.
once they get the confidence in doing that.
Yes, Dylan.
Just a quick point there. In finding the gradient of the line is possibly a really excellent opportunity to start discussing change
Yes.
in speed over
Yes.
change in time.
Absolutely.
Because then they don't necessarily need to remember the Y1, Y2, or the Y1, Y2 algorithm. Just makes a little bit more sense.
Absolutely, because let's see, what are we looking at over here? Sorry, I need to go. Where were we? Yep, there, on that graph. Okay. So originally from this graph over here, which was displacement time.
Yes.
A displacement time is change in y, change in what is on the y-axis, divided by the change in the time on the x-axis. So what is change in displacement or rate of change in displacement? It is your definition for velocity.
Okay.
So you're then going to get the velocity from taking change in displacement over change in time.
Okay.
Looking at the next beautiful data that we've got over there, same thing. This is a graph of velocity versus time. So what is change in velocity divided by change in time? It's acceleration. So I've now got acceleration. How do I calculate acceleration? From the gradient of a velocity time graph. And to spend the time embedding these concepts in students, not just getting them to plot the graph and gather data, and get the answers. This whole exercise is not about the answer. It's about the connections that they make in the process. Yeah. So now going on to what I said as one of my teaching things is use the same data to carry through a position time graph, a velocity time graph, and an acceleration time graph ultimately.
And that's what you've done here.
And that's what I've done here. And as you can see, I've made this data fractionally more pretty. All right, so we've got nice 10-minute intervals going there, and we've got kilometers. I like this particular exercise because it forces them to be reminded about conversions.
Okay.
Minutes, we don't have such a thing as meters per minute or kilometers per minute. We have to go either into seconds or into hours. What is 10 minutes of an hour? It's 1/6 of an hour.
Okay.
What are we going to be working in? We're then going to be working in kilometers per hour. So there's the whole practice while we're going slowly and pedantically through things of unit conversions and understanding the need for compatibility between units.
In grade 9 maths, you tell them, okay, we're converting units now, but you'll never have to do it again. So just do it until this exam and it'll be fine. And
you liars! Horrible people! Okay. Now comes the slightly more tricky bit.
Yes.
So we'll plot that graph, which is not too bad. It's a displacement time graph. We can get the velocity or speed by saying the displacement, change in displacement over the change in time. And again, we work through it nicely and slowly. The next part is what becomes difficult, is they now need to use this data to work out the velocity at certain points.
Okay.
Right. So they are going to go from 0 minutes to 10 minutes, and the difference in time is going to be 1/6.
Okay.
So it's change in displacement over change in time.
Why is S used for displacement?
Your guess is as good as mine.
Okay.
Okay, I think D had been taken. I don't like it.
No.
And then, you're talking about speed and you're using V. And even before you've taught velocity in grade 9, you're already using V as the symbol for speed, and they don't know why. I would love it if we were sort of distance or displacement D is equal, but it's not like that.
Yeah.
So it's just something they have to get used to. It adds one more layer to the potential for confusion, and I like to take those layers away if I can.
Yeah.
But this is not one of the places where one can. Right, so we get to 120.
Yes.
But where is that true? That isn't true at 0, and it's not true at 10 minutes. It's actually true at 5 minutes because we've just calculated an average velocity there. So when I'm going to plot a point, I need a point, a single dot. So I can't say over the period 1 to 10 minutes. I have to choose a point, and that's at 5 minutes. So that's 1/12 of a second. Oh, sorry, going ahead. So that's at 1/12.
Okay.
And each time I have to go in between. For my velocity calculation, I need to choose the point in between. This is really great when you start teaching ticker timers, as I like to, afterwards.
Yes.
Because again, they need to understand that concept of a midpoint for an average.
Annabelle, we've got roughly 6 minutes left.
Okie dokes. All right. So
just so you're warned.
Not a problem. So we're going to take that data and we're going to convert it then into a velocity time graph. Again, they can work out the gradient here and find out that the gradient is 0 because this object did not accelerate. So that's quite nice. And you can work out the area and find that you beautifully get about 180, which is as close as anything to 179 meters.
Magic.
So it really does concretize them. This is another example which is almost identical, except for the fact that we do have acceleration here.
Yes.
So the position time graph actually takes a curve,
Okay.
and then that converts into a straight line velocity time graph, which ultimately is going to be a constant acceleration.
Okay.
All right. I really want to play with my moving man.
Yes, your moving man is loaded. So if you press escape
Okay.
and go down to the start bar, you'll find him hiding underneath there. Now, your moving man is a FET simulation.
It is a FET simulation, an absolutely wonderful initiative by the University of Colorado.
Yes.
They are completely free of charge. They have one big drawback in our current system, and that is that they cannot work on a smartphone or on an iPad. They are written in Java and can only work on a computer. So
dear.
in terms of, you can't just grab the child's smartphone and then be able for them all to interact. You still need to go to the computer lab like we did long ago and interact with it like that. There is a big fundraising effort, and they are trying their best to convert their Java material into HTML. And there's one application that I found so far that does work like that, but this is not one of them.
Okay.
Okay, so just to be aware of that.
Yes.
So we've got this little man over here. He's not so exciting until we look at his graphs. And he can move around. Look at him. And he can do all sorts of things, which is quite fun and funky. We'll stick him. If you don't mind, I'm going to move him back and then I'm going to clear everything.
Okay.
And we're going to pause him. I'm then going to choose a constant velocity for him. And let's make it 2 just because that will work. And we keep him going at a constant velocity. His position
That is very nice.
increases and his velocity stays constant and his acceleration is 0.
Yes.
And we can see all of those graphs growing before our eyes.
That's
and then he hits the
fantastic.
wall, and that's the end of the story.
Yes.
So he doesn't have very far to go between his tree and his house. The other thing that we can do with him is we can play with acceleration values. So we can just make that 2 because 2 is a nice number. And we can again, let's bring him back because otherwise he's going to stay on the wall. Come, Mr. Man. And we're going to send him off. Let's clear everything again so that it looks nice. And again, go with 2. And now what I can see is I can clearly see my velocity. He's hit the wall again. But we can clearly see my position time graph shape. And I can clearly see an acceleration. You can play with these axes. I can't do it now. But I can play with the axis and bring it down.
So you're zooming into
I'm
it.
zooming. So there we go. So I can now see that he was accelerating at a constant 2 meters per second squared.
Okay.
So that's the one that's really cute. And the other one that's really cute is this one, which looks pretty similar, but it's about you pushing something. So I'm not so fond of pushing the filing cabinet. I quite like to choose the textbook to push and then to look at graphs of position, velocity, and acceleration, and then give this one little shove. And with one turn off the friction. And it's quite nice if the friction wasn't off because the friction made it stop.
Okay.
So let's just put that book. Woo! Come back. Clear. I'm sure I'd like to reset everything. Yes. Okay. And I want my friction off. And now I'm going to apply a force and see what comes out of that.
And of course, if it's a frictionless environment, it'll
It'll
carry on
going forever at the identical velocity. And look how nice that is. And then put friction in and play with that a little bit. The other thing that I can do is I can choose an applied force. Remember what a force means? It means there's going to be an acceleration.
So this will tie in nicely with Newton.
And I've used it to teach Newton as well. And it's a lovely introduction to Newton in the sense that you revise your grade 10 graphs of motion before launching into Newton so that they've got that foundation nice and solid.
It's always good to revise, isn't it?
Super.
Yeah.
So here, let's just pop a number in. and go, and that force is constantly being applied, and the kids can actually see how that thing is speeding up. And we can see the position time graph getting a curve, and we can see the velocity time graph is constant, and we can see the acceleration time graph is horizontal.
So you're proving your point.
Over and over, and letting them play, because,
Yes.
again, they love it. So after actually drawing graphs, to have a little play and see that it happens, and they have the options. Oh, and there's nothing they like more than using the sleeping dog.
Yes.
Yeah. And then to also, play with the heavier objects, stick some friction into there. And when you're doing Newton, also to look at some of the forces that are at play.
Okay. You have a list of good ideas for us.
I have.
Yes.
Do we want to just get there?
Yes.
I'm sure.
Okay. And press present for us.
Thank you.
And there we go. First good idea says demonstrate ideal data collection.
Okay, let your teacher give you nice numbers that are going to work.
Yes.
And that's my first. I really think that you are, and I'm talking again about that, taking away possible misconceptions.
Yes.
Where if there is stuff that you can unconfuse the students with, let's do that. And so when introducing concepts, don't start with unless it's a beautiful investigation that you know is going to give you reliable data. Rather, give them reliable data. These are, after all, high school students.
Yes.
They're not postgraduates, The next one is allow time. I set aside a week for this exercise of spending time going around the classroom, as we were saying earlier, interacting, helping each student plot that gradient on one or the other of the graphs. Later on, when you're doing the change in position with acceleration, what is a tangent to the curve? How will you then get a gradient from that?
Tangents much later in maths.
So tangent, it's not that difficult. It's a point that touches a line that touches the curve at one point. But once they've got that, just that you're probably not going to have to calculate it, but they need to conceptualize it. And it takes time with grade 10s. This doesn't fly through. And finally, allow students to start gathering their own data and then try and plot that. And then unpack discrepancies. Unpack why it's not all looking like it should. Because they're only going to be able to answer lower order questions of having been able to plot ideal data.
You're stealing my points from me because I was
so
about to
sorry.
say that's what... Yes. Now, we wanted to talk about the overhead projector, the use of overhead projector, and then we didn't get to it. But I do want to make the point that it is one of the most underrated tools in the classroom, especially with graph work.
So much, because, again, can I just do a quick demo with this?
Yes.
If I'm sitting on my blackboard or my whiteboard or whatever, and I try to put a graph up, invariably accuracy is going to be lost. I'm not going to have straight lines. So much better to have a transparency up, to be able to actually show students how you're plotting points, to actually have them visualize exactly what you're doing, and that you show them the process of drawing, the process of interpretation.
Yes.
What I have is a whole lot of these. So I've actually printed transparencies just with blank graph paper. You can always wash them afterwards if you use water-soluble pens. And then just that you plot onto the graph paper, and there's less guesswork for the students. They're seeing what ought to be happening on their own page, not some inaccurate version of it up on the board.
What's also nice is that you can flip between them really easily.
Oh, it's really, really nice. And that you can go and say, okay, so you can see that is, they're fairly deep.
That's
in
a
this
straight line, but the other one's curved.
Correct. So
do you remember the one we did 10 minutes ago?
Correct.
You haven't erased it. It's right there.
And so here's the displacement time graph of the same data for the velocity time graph, and we can easily go between those two.
Yes.
I also like it when I teach more than one class. Sometimes I don't have to write something out all over again. And it's outstanding for discipline. We were talking about discipline at the very beginning of the session. And we were saying that moving in among your students gives you better classroom management. The overhead is another awesome tool for that because you face the class. There's no space for them to get up to nonsense because you're looking at them. And I've actually mastered the skill of being able to write on the overhead and still see what Dylan is up to.
Wasn't me, I promise.
So it really does empower teachers, especially as you're starting out, to make sure that you are in control of that space that you have created. Yeah.
Yeah. Okay, Annabelle, we are out of time. We've actually gone over time.
Okay.
But it has been wonderful having you. Thank you for coming in.
It has been such a pleasure and so much fun. Thank you very much for having me.
And thank you, Dylan, for
Thank you,
your
Dylan.
behind-the-scenes magic.
Yes.
And we'll see you again next week. Goodbye.
Goodbye.
Created using Powtoon.